Welcome to Lecture 4.9, Variation of Parameters for Systems. This is the third lecture on variation of parameters that we've seen, so I want to begin by reviewing the big ideas from the first two lectures, which were on using this method to solve first order and second order ODEs respectively. There's a reason why these are all the same name. It's because it's the same fundamental idea, the same technique. So variation of parameters, you should think of it as a last resort method for finding a particular solution to an ODE. So for a first order ODE, I should say first order linear ODE of the form y prime equals p of ty equals f of t, the first step is always the same. Solve the homogeneous equation first. That is, set the right-hand side equal to 0 and solve for yh. And by the fundamental theorem of differential equations, there is a one-parameter family of solutions. So we'll say that yh of t is some constant c times y1 of t. Now, y1 of t has the form e to the negative integral p of t dt, but this is probably not how you learned it or know it. You don't memorize this as a formula, rather you just take the ODE and just separate variables. So let me do that for you right now. That's dyh dt equals negative p of t yh. And if you separate variables, you get dyh over yh equals negative p of t dt. And if you integrate both sides, then the left-hand side is just the natural log of y. And so to solve for this, you just, or so should say yh, and then you just exponentiate both sides. And this left-hand side is yh. So that's where this comes from right here. Okay, so this is the first step, always, for both first and second order. Solve the homogeneous equation. The second step, then, is find a particular solution. And the variation of parameters method says that the way to do that is to take your homogeneous solution and multiply it by not a constant, but by a function, v of t, and then solve for v of t. Turns out that v of t has a closed form solution as well, namely v of t is the integral f of t times e to the integral p of t dt, all with respect to t. Now this is the first time that I'm showing you this formula because it's not really that useful. This is not how you should be using this method, but rather you should just be taking v times y1, taking the derivative, you got to use the product rule, plugging it back into the ODE, and then solving for v of t. Now, I'm showing this to you. I think it's helpful after the fact to see this formula because then you can see when this method works. So this method works, well, this method always works assuming you can first of all actually solve the homogeneous ODE, and you always can. I mean, you get this formula. The one thing that could go wrong is maybe you can't integrate p of t. There are some functions that don't have closed form integrals, but even in that case, you could still write your solution as the integral and just leave it like that. And finally, the next thing that you need to be able to integrate is this f of t times this function here. And if you can't integrate that, again, the worst case, you still have a solution, you just might have to leave it in the form of an integral. So this method always works. And solving the homogeneous, there's other methods that start out with this too. So really the utility of the variation of parameters method is that it will give you a particular solution. It's a recipe for one that will always work. Again, in the worst case, if you're okay with just leaving it in the form of integrals. Next, let's compare the first order method to the method for solving a second order linear ODE. That is of the form y double prime plus p of t y prime plus q of ty equals f of t. So the first step is the same. You solve the homogeneous ODE first. In other words, you set f of t equal to 0 and you solve. Since this is a second order ODE, we get a two-parameter family of solutions. That is of the form C1y1 plus C2y2. Now, solving the homogeneous equation is harder for second order ODEs because we can no longer separate variables. And sometimes we can't do it at all. So remember how this worked. The simplest case was when P and Q are constant. In that case, we look for a solution y of t equals e to the rt and find r. If P and Q are not constant, then, well, if we're lucky, and this is a Cauchy-Euler equation, then we might look for a solution of the form t to the r, but again, that's just a very special case. So if we're not that lucky, then we have to look for a power series solution. So that is a n t to the n. We used x, but we got t here. Or if we have regular singular points, we have to look for a generalized power series solution, a n t to the n minus r. And here I'm assuming centered at 0, but it really, you can do it centered at something else. But if we have an irregular singular point, then we really don't have a solution for this, and we're stuck, and we can't go on. So the variation of parameters method, again, the crux of this is not solving the homogeneous equation, but it's a way to get a particular solution. For a second order ODE, there's a particular solution of the form v1y1 plus v2y2. This is in some sense a generalization of just v times y1 above. Now, what was not obvious at all when we did this, why this should work, but it did. And again, we had to plug this back, we had to take derivatives, plug this back in, use some little magic, and we got formulas for v1 and v2. And I actually showed you these formulas, unlike what I did for the first order case, because in this case it was actually useful to have these things. It wasn't quite so simple to just take derivatives and plug it back in like we did with the first order. So v1 was the integral of negative y2 times f divided by this curious product, which is something that we called the Wronskian. So that's, remember that? It was the determinant of y1 of t, so of the matrix y1 of t, y2 of t in row 1, and y prime of t, y1 prime, and y2 prime of t in row 2. So this was called the Wronskian. And remember that this thing was equal to 0. So this method does not work because you're dividing by 0 precisely when this determinant is 0, which is when y1 is a multiple of y2. Now this seems like a silly thing to do, to compute, just to check that y1 and y2 are multiples of each other, because you can just check that directly, and in some sense it is. We did not actually need this Wronskian for that lecture. However, it does come up in this lecture and in other areas in differential equations, so I will mention it again, and I will show you in this lecture how this is actually a special, this whole second order method is a special case of solving a 2x2 systems using our new variation of parameters method, which will be a generalization of this method. Okay, so v1 is the integral of negative y2 times f over the Wronskian, and v2 is the integral of y1 times f over the Wronskian. To summarize, this variation of parameters method always works, assuming that you can actually find the homogeneous solution and evaluate the above integrals. I call it a last resort because it's usually one of the harder methods. For first order, if you can, well, integrating factor is about the same, but if you can solve the homogeneous and find a particular solution by inspection, that's easier. And for second order equations, we like to use that, I think I called it undetermined coefficients method. Again, guess and check to find your f of t, but you can't always do that, especially if you have a function like tangent of t. So this is a good last resort method that will work. Now that we've reviewed the big ideas of these methods, Now that we've reviewed the big ideas of these methods and the structure of the solutions, both the form of the particular solution and the actual answer, I'm going to take you into the general method for 2x2 systems. And as we'll see, that this second order method is really just a special case of the general method. Okay, so let's do that now. Consider a linear 2x2 system of ODEs of the form x prime of t equals a of t x of t plus b of t. Now notice here I am not restricting to the case where the matrix A and the vector B have constant entries. These are allowed to be functions of t as well. The first step, no surprise here, is to solve the homogeneous equation. That is, xh prime equals a times xh. If we do this, we get a solution of the form c1x1 plus c2x2. So a two-parameter family of solutions as before. Now, I haven't shown you how to do this in the case where A depends on t, and I don't think I'll put that in this class. We have enough material to cover anyways, but it's something that you can easily look up if you ever come across it. Okay, now c1x1 plus c2x2. Now x1 and x2 are vectors, so I'm going to write these in vector notation. I'll write this as c1 times the vector x11 on top and x12 on the bottom, and c2 times x21 on top and x22 on bottom. And now in matrix form, I can write this as the matrix of these entries, x11, x21, x12, x22, times the vector C, consisting of entries C1 and C2. Now one quick comment. Normally when we write matrices with indices, we write x11, x12, x21, x22. In other words, the indices as integers are in increasing order as you would read them from a book. Here we have swapped the 2, 1 and the 1, 2. So some books might call this matrix something like xh transpose, which is what you get when you swap these two entries, but I'm just going to call this xh. So this matrix is going to be xh, and it's a little bit unusual to have this ordering of the indices. But I think it's important because it comes from this vector being the entries for x1 and these entries coming from x2. As before, the utility of the variation of parameters method is that it will find us a particular solution when we need it. So in this case, we assume that there is a solution of the form xp of t equals the homogeneous solution xh in matrix form times v of t. So in other words, that's xp of t equals v1 times our first solution, x1. Notice that is a scalar function. This is a vector function, plus v2 times x2, which in vector notation is v1 of t times the vector x11, x12, plus v2 of t times the vector x21, x22. And in matrix form, this is just the 2x2 matrix xh of t, where the columns are x1 and x2, times the vector v1, v2, which I'll call v of t. Now, even though I just did it in the previous slide, I really want to emphasize how similar this is to both the first and the second order cases. So this solution here, recall we did for first order ODEs. We had yp of t. It was the I'm going to write it slightly differently. The homogeneous solution, yh of t, times v of t. And now recall what we did for second order ODEs. There we had yp of t equals v1 of t times y1 of t plus v2 of t times y2 of t. And that is completely analogous to this. So in some sense, this is completely analogous to both the first and the second order case, depending on whether you write it in matrix form or in vector form like this. Okay, now that we have the correct form of a particular solution, let's actually plug this in and figure out what v of t has to be. Or if you don't believe that this, or if you're skeptical that this works, this next step will confirm it. Okay, so of course our next step is to just plug in. So how defined xp of t, and the answer is just plug xp, which is xh times v, into the ODE x prime equals ax plus b. Okay, so let's do that. So xp prime, so we have this product here. The derivative, we have to use the product rule. That's just x h prime times v plus x h times v prime. And then the right-hand side, we just have to plug this in for x here. So this is a times this product plus b. So that is a times xh times v plus b. Now what I want you to notice is that since xh solves the homogeneous equation, the derivative, or I should probably just box it without the v, xh prime equals a times xh. So these two things, put an equal sign here, are equal. Now you may be a little bit skeptical because this is a matrix and not a vector, so why can I plug a matrix into this? And I completely understand that. So if you are curious, the reason is because the derivative of this matrix, I'm going to write it, so this is a 2 by 2 matrix, so really I can write this as a matrix of 2 vectors. So this is x1 prime and x2 prime. And because x1 and x2 solve the homogeneous equation, I can replace x1 prime with a times x1. So I can write this as the matrix of the following two columns, a times x1 and a times x2. And this right-hand side, this is precisely what this is a times the matrix x1 times x2, which is a times xh. And then this equality is because x1 and x2 solve the homogeneous equations. So in other words, this x1 prime equals ax1 and x2 prime equals ax2. This is just a different way to write this matrix is a times xh, and so that's why these two things are equal. So of course if these two things are equal, then if we multiply them by v, they're equal as well. So in other words, for this equality to hold, what we have to have is that this term xh times v prime has to be equal to b. So let me write that. So that implies that xh times v prime equals b. Okay, so this is something that we know how to do. So all we have to do is multiply the left and right hand side by the inverse of xh, and we get our solution that let me do that again, that v prime equals xh inverse times b. And so we get that, of course, from here we can just integrate both sides. And so we get that v equals the integral of xh inverse times b dt. So in integrating a matrix or a vector, we're just integrating term by term. And we will do 2 examples of this. So if you're a little overwhelmed by the symbols here, that's fine. But you should, hopefully every step you're able to verify that this does make sense. Okay, so quick comment. This matrix A has to be invertible because, remember, the homogeneous solution means that these 2 things are not scalars of each other, which means that the Wronskian of this matrix, the determinant of these 4 things, has to be non-zero. Because the determinant is non-zero, the inverse exists. Now, technically, I should say, I'll just say this without writing it. You have to be careful because these things are functions of t. It could be the case that this determinant is 0 at a couple points, like a few roots, but not everywhere. And in that case, we can't do this. So generally what happens is you assume that this is non-zero, you assume that the determinant is going to be let me draw it up here, is non-zero at the origin, and then there is some particular amount of time where the determinant is non-zero as well. Maybe plus or minus around the origin, although we usually start at 0. So if we have a few points in time when we have the determinant is 0, this is not going to be defined, and so our solution is only defined up to that point in time. Of course, it could be defined everywhere if there are no such values of t. So these are technical details that we have to deal with if these are in fact functions of t. If these are, of course, if these are constants like all the cases we've seen so far, this is not something we have to deal with. Okay, so moving on from here, let's actually expand this a little more. So I'm going to write this as v of t equals the integral, I don't know how big to make this, is the integral of the inverse of h. So this is 1 over the determinant of this matrix, so that's this cross product. I'll write, so that's going to be 1 over x11 times x21, sorry, 22 minus x12 x21. So that's this, remember that this product minus that product. And then remember how else you find the inverse of a matrix? You swap these 2 rows and you put negative signs in front of these 2. So I'll put that matrix, so I'll swap those 2 entries, not rows, swap those 2 entries, so x22 times x11, and then negative x21 and negative x12. Okay, so right there, this is the integral of the inverse of xh, and then times b. I haven't actually given entries yet. Let's write b1 and b2. These could be functions of t. This is a function of t, but I'm omitting all of my of t's here, just for clarity. And once again, this thing at the bottom, this is the Wronskian, and I'm going to call this W. I think I might have used this notation in a previous lecture. I don't remember. The Wronskian of the vectors x1 and x2. So that's what this is. Okay, so now what we have is we can, let's see how we want to do this. So it's the integral of 1 over the Wronskian of x1 and x2. Now let me just, for simplicity, just multiply this out. I could skip steps, but it's easy. I'll probably make a mistake if I do. So x22 b1 minus x12 b2, that goes on top. And then on the bottom is negative x21 b1 plus x11 b2. Again, all I did here is I'm multiplying these rows times, so this is this row times this column, and this down here is this row times this column. I should probably put a dt in, I'm integrating, I should probably put a dt in here somewhere. Let's see, where did I There we go. dt goes there, and then dt goes there. Okay, so now I don't know if I could fit this in here. We'll try. This as a vector, the top entry is just we can bring the integral inside. So it's the integral of this. So let me see. So that's the integral of x to 2 b1 minus x11 times b2 over the Wronskian w of x1 and x2. This is dt, and then let's add a c1 just to remind ourselves that there is a concept of integration in here. And then the bottom is the integral of x11 b2 minus x21 b1 over the Wronskian x1 and x2. This is dt plus c2. Okay, so this is a formula for the solution. And you know, I think that unlike the first order case when I said don't memorize the formula, because I didn't tell you till this lecture, I think it's actually good to memorize this formula. I think it's good to jump to the very end right here. I guess it's not too hard to go from here to here, but it's harmless to go from here and then just plug things in, plug and chug, and end up here. So I encourage you to pause this lecture, go back a slide, and compare this to the formula of the 2x2 cases when we had v1 and v2 explicitly written. And once you do that, come back and we will do two examples. One of them will be an explicit example for a particular matrix A and B, and the next one I will show you how to turn an arbitrary 2x2 system, or an arbitrary second order ODE, into a system of first order ODEs, and to use this method, and we'll see why what we got in the previous slide is actually a special case of this. Here's our first example. I want to solve the initial value problem. X prime equals ax plus b, where a is the matrix 1, negative 4, 2, negative 5, and b is the vector 10 cosine of t and 2 e to the negative t, and we have an initial condition x of 0 equals the vector 10, 4. So this is something that we do not know how to solve at this point. We know how to solve the homogeneous part, but we have never seen an ODE where the inhomogeneous part, b of t, is not a constant. So previously what we've done is we've just said that to find a particular solution, we just take a steady state solution, which was A inverse B. Now we set this equal to 0 and solve for x, but that only works when there is a steady state solution. And if this is not constant, then this doesn't work. This so-called steady state solution depends on t, and therefore it's not a steady state solution. In other words, the derivative of it is not 0 to begin with. Okay, so I am not going to actually solve the homogeneous part for you. I'll just tell you what it is, because at this point we should know how to do it. So I'll just tell you that the homogeneous solution is c1 e to the negative t times 2, 1 plus c2 e to the negative 3t times 1, 1. So in other words, the eigenvalues are negative 1 and negative 3, and the eigenvectors are 2, 1 and 1, 1. Okay, so in matrix form, we're going to make this matrix, the homogeneous solution matrix, xt, is we're just going to put these, so we can bring these entries inside and set the constants equal to 1, and we get 2 e to the negative t, e to the negative t, e to the negative 3t, and e to the negative 3t. So once again, that's 2, 1 appears here and here. E to the negative t appears in this first column, and the second column is 1, 1 times e to the negative 3t. Okay, so now let's find the inverse of this. So the inverse of this matrix is 1 divided by the determinant, or the Wronskian. Now that's just this product minus that product. So that's, see, 2e to the negative t times e to the negative 3t. What is that? That is 2e to the negative 4t, right? Minus the product of e to the negative t and e to the negative 3t. So that's minus e to the negative 4t, which together that's just 1 e to the negative 4t. Okay, so now for the inverse, remember we swapped the entries. We swapped the position of these two things, and then we put negative signs in front of these. I'll just put that there to remind you without actually putting the negative sign. Okay, so in other words, we get e to the negative 3t on the top left and 2e to the negative t on the bottom right. And then we have a negative e to the negative 3t in the top right and a negative e to the negative t in the bottom left. So this thing, of course, is just, or this whole thing, 1 divided by e to the negative 4t is just e to the 4t. Okay? So all we do is we just multiply e to the 4t times each of these entries, and what we get is we get e to the t up left, we get negative e to the t in the upper right, we get negative e to the 3t in the lower left, again e to the negative t times e to the 4t. In the lower right, we get 2 e to the negative t times e to the 4t is 2 e to the 3t. Okay, so that's our XH inverse. So now our particular solution, xp of t, put a vector on that, is this homogeneous matrix. So actually, I should probably remind you that xp of t is the homogeneous solution times v of t. Yeah, that's important to put up there. So last time we actually finished with just the formula for v of t. I didn't multiply it again by here, by xh, but we have to now. So our particular solution is this matrix that we just found up here times v, which we know is the integral of xh inverse of t times b of t dt. So recall that this thing here is v of t. Okay. So we had a formula for that, but the previous slide, let's not use it. Let's just plug in xh here and b here. It's not really any harder to do. Okay, so xh is, so this first term, xh, that's this up here. So I'm going to write that in blue. So that's 2 e to the minus t, e to the negative 3t, e to the minus t, and e to the negative 3t. And then I'll do the rest in red. It's the integral of the matrix e to the t, negative e to the t, negative e to the 3t, and 2 e to the 3t, times the vector 10 cosine of t times 2 e to the minus t dt. Okay, so let's see. I'm going to move over to the left. I'm going to rewrite this same matrix in blue, xh. I don't need to say it out loud because I'm just copying. I'm doing it one step at a time. The minus t. What I will do is multiply this matrix xh inverse times b. So the integral, so what is that? So on top, that is 10 e to the t cosine of t minus 2. And on bottom, that's negative 10 e to the 3t cosine of t plus 4 e to the 2t. dt. So I did that a little quickly, but I actually did that on scratch paper that I'm looking at right now. It's just this matrix times this vector. There's nothing hard or tricky about that. Okay, so now let's integrate term by term. Something else I also have on scratch paper in front of me, because integrating this is one of those nasty integration by parts where you have to do it twice. Remember those from calc? Yeah, so I actually just plugged this into Wolfram alpha, and I got that this is equal to, so that same matrix, xh, let me just recopy that in front of me. But now integrating this vector term by term, and the top ends up being 5e to the t sine of t plus cosine of t minus 2t. And the bottom is negative e to the 3t times sine of t plus 3 cosine of t in parentheses plus 2e to the 2t. So now if we simplify this, so if we multiply, now we have a 2 by 2 matrix times a 2 by 1 vector. If we multiply this out, what we end up getting, also it's these two rows times this column. I've done the work on the side, and I'm just reporting what it is. Trust me, it's not that interesting. You get 7 cosine of t plus 9 sine of t plus 2 minus 4t times e to the minus t on top, and on bottom you get 2 cosine of t plus 4 sine of t plus 2 minus 2t e to the minus t. So that is our what was that? That was our particular solution up here. So our final solution is, actually, let me do this. I'm going to put a line here, and I'm going to say that our final solution, our general solution, is x of t equals our homogeneous solution, x h of t. That's a vector form of both of these, not matrix form, plus xp of t. And that equals, so here's xp of t right there. And now my homogeneous solution is up here. So I'll do that first. So again, this is xp. And then plus the homogeneous solution is c1 e to the minus t 2, 1 plus c2 e to the minus 3t 1, 1. So this is our final solution right there. That's our general solution. Now I shouldn't say final because I actually gave you an initial condition. So if you use that initial condition, what color should I use? So I'll try to squeeze this in here. We'll use the initial condition. So let's see. X of 0. I'll just tell, I'm not going to rewrite the whole thing. I'll just tell you what C1 and C2 are. So x2 of 0 is our x of 0. Let's see. So if you take this whole creature and you plug in 0, over here you get a 7 times. So you got a 7 here, a 0 here, and a 2 times 1. So you got a 9 up here. So you got a 9 up top. On bottom, if you plug 0 in for 2 cosine, you get 2. 4 sine, you get 0. And then 2 minus 2t times e to the minus t, you get a 2 times 1. So you get 2 plus 2, that is a 4. So 9 is 4. And then if you of course, if you plug t equals 0 in for these two, you get a c1 2 1 and a c2 1 1. So plus c1 2 1 plus C2, 1, 1. Okay, and you set that equal to 10, 4. Okay, so now this is just a standard 2 by 2 system that we know how to solve. I can subtract it 9, 4 from 10, 4. And what I get is, what's left is 2, 1, 1, 1. This matrix times C1 times C2 equals, again, 10, 4 minus 9, 4 is the vector 1, 0. And if you do that, you solve this, it's easy to check, you get C1 equals 1 and C2 equals negative 1. So our final solution is, I'm not going to rewrite it, it's just this thing in green where this is C1 is equal to 1 and C2 is equal to negative 1. Okay, so thank goodness that's over. Okay, so as promised, we will now solve a general second-order linear ODE by turning it into a 2 by 2 system and using the variation of parameters method that we just learned. And in doing so, we will get a solution that matches the solution that we got when we learned variation of parameters for second-order ODEs. Okay, so here's an ODE, y double prime plus p of t y prime plus q of t y equals f of t. And to turn this into a second order system, remember what we do here is y, we're just going to call this x1. And so think of y as like position, which is x1, and then velocity, instead of calling that y prime, we're going to call that x2. And in doing so, y double prime, we don't get a second derivative, we just get a first derivative of velocity, or of x2. Okay, so let's write that down. I'm going to let x1 equal to y, and x2 equal to y prime, which is just equal to x1 prime, if you prefer. Okay, so now this gives us a system of, so what we want to do is we want to write x prime equals a x plus b. So to do that, the left-hand side, x prime, corresponds to a system x1 prime and x2 prime. So let's see what that system is. So x1 prime equals x2. So that is, I'll leave a gap here, x2. And then x2 prime. So x2 prime is just y double prime. So x2 prime. Well, what do we want to? How do we want to? Let's write it down here, or how about up here? So x2 prime equals negative q of t y minus p of t y prime plus f of t, and of course this is just x1 and that is x2. So x2 prime equals negative q of t x1 minus p of t x2 plus f of t. So if you want to fill this in, you can say this is plus 0 and plus 0 x1. So in matrix form, this is x1 prime, x2 prime equals 0, 1, negative q of t, negative p of t, x1, x2, plus 0, f of t. Okay, so now let's consider two solutions to the homogeneous equation. So let me write that down. Consider two solutions to the homogeneous equation, and let me just emphasize that this is x prime equals ax plus b. And actually, this is the first time that we have seen a system x prime equals ax and solved it where the matrix A is no longer constants, or consists of only constants. So consider two solutions. Let's call one of them x1 of t, x1 of t. So this is going to be a vector of two functions, x11 of t, x12 of t. And by definition, since this is a vector of x1 and x2, x1 is some function y of t, I'll call it y1 of t, and x2 is its derivative. So y1 of t comes up here, and y1 prime of t comes up here. So notice that by construction, y1 of t solves the homogeneous version of this ODE. And finally, we have x2 of t, which is x21 of t and x22 of t. So if we have a solution like this, it is of the form some function y2 of t and its derivative y2 prime of t. And here, y1 of t and y2 of t solve yh double prime plus p of t yh prime plus q of t yh equals 0. Okay, so we can find two solutions like this just by solving this as we've done before. Okay, so now we have that homogeneous solution matrix. So now xh of t it's the matrix where this is the first column, that's the second column. It is y1 of t, y1 prime of t. Well, I don't know why I'm writing the of t's. y2 of t, y2 prime of t. This should look familiar. Oh, and b of t, of course, is 0 and f of t. Okay, so several things. Now, if you want to, you can just use the formula that we've derived to solve this, but I want to say a few remarks. Oops. So one remark is that the determinant of xh here is just y1, y1 prime, y2, and y2 prime. That is the Wronskian of this fundamental set of solutions, y1 and y2. Remember the very first slide, and we saw it in a previous lecture too. I came up with this matrix, and I said, yeah, the y1 and y2 are a fundamental set of solutions if the determinant is non-zero. Well, now we've seen a more general form of the Wronskian on the previous slides, but in the special case where our system here comes from a second order ODE, our Wronskian is how we originally saw it, where we have our solutions here and their derivatives right there. So that's one remark. And another remark is that when solving this, remember how we got xh times v prime equals b? Remember that? And of course, from there, this is how we found v. We said that v prime equals xh inverse times b, and then we integrated. But let me just hold off and stop right here. And if we write this in matrix form, this should look familiar. y1, y2, y1 prime, y2 prime, times v1 prime times v2 prime equals 0 and f of t. Now let's write this in your standard, or in bracket notation. This is just y1 v1 prime plus y2 v2 prime equals 0. and y1 prime v1 prime plus y2 prime v2 prime equals g of t. Now, if you remember this, you may not, but if you don't, go back and look at the end of the second variation of parameters lecture. When in that lecture, I write that we're going to find a particular solution of the form v1 y1 plus v2 y2, and then from that I make the case why we get this first equation, or we get one of these equations, and then the other one I sort of hand-waved. I said, well, we need a second equation, and it should make sense that this will work, but I didn't really justify it more than that. I had a weak justification, but these equations you have seen before. You have seen those at the end of that lecture. This is how we solved second-order ODEs with the variation of parameters method, by coming up with these two equations and solving them. And here I'm just showing you that using our more general method of systems, in the special case where the system comes from a second-order ODE, well, the special case of this very important equation that we've seen is just this same familiar system of two equations. Okay, so I'm not going to solve it. Well, let's see. I don't know if I even have room for this. Tell you what, I'll solve it right here. So if you solve for this, if you solve for v1 prime, I should have thought ahead. So if you solve for v1 prime, let's see. So you subtract this to the other side. You divide. I'll just write that v1 prime of t equals negative y2 of t times f of t divided by the Wronskian of y1 and y2. And you get that v2 prime of t equals y1 of t f of t divided by the Wronskian of y1 and y2. Okay, so if you actually solve the algebra here, then this is what I'm not doing it here because we did it in that previous lecture. If you solve this algebraically, you get v1 prime and v2 like this, and then you integrate, oops, I'm using the wrong pen, you integrate both sides, and that's where we got our solutions for v1 and v2 in their previous lecture, which I summarized on the first slide of this lecture. I began with the summary, and now I will end with the summary. The variation of parameters method finds a particular solution of an ODE of the following form, depending on which case we're in. So for first order, we find a solution of the form v of t times y1, where y solves the homogeneous equation. For the second order, it finds a solution of the form v1 y1 plus v2 y2, where y1 and y2 solve the homogeneous equation. And for a 2x2 linear system, or actually an n/n system, it finds a particular solution of the form the matrix homogeneous matrix XH times v of t, where the columns of the matrix are the solutions of the homogeneous equation. And we did 2x2, but this works for 3x3, 4x4, and so forth, as long as you know how to take inverses. Now, I want to remind you that for this 2x2 case, we saw that if you multiply this, write this like in vector form, this is actually equal to v1 of t times x1 of t plus v2 of t times x2 of t. So this really is the same as this as well, the second order form as well. So depending on whether you think of it as a matrix form or in vector form, it's completely analogous to both of these. This is all the same method. Both of these are really special cases of the n/n case of what we just learned in this lecture. We saw in this lecture that in the 2x2 case, this xh times v is xh times the integral of the inverse of xh times b of t, where b of t is the inhomogeneous or the forcing term. It's not the first time we've seen it, but we also revisited the idea that a second-order linear ODE can be rewritten as a system by setting x1 equal to y and x2 equal to y prime, which gives us a system x prime equals a times x plus b. Now, even though we've done this previously, in this lecture we showed that if we do variation of parameters for systems, on this special case, we recover exactly what we got previously when we generalized variation of parameters from first order to second order. So some final remarks. This method is the only way that we know how to find a particular solution of a non-autonomous ODE. In other words, x prime equals ax plus b of t. If b depends on t, there will not be a steady state solution, so we need to find a particular solution using this method. This method also works if the matrix A of t is non-constant, but we first have to be able to actually find the homogeneous solution before we can find a particular solution. Finally, such a solution above is only defined if this inverse matrix exists. In other words, if the Wronskian is non-zero. So the general Wronskian is of this form, where the columns are x1 and x2, and in the special case of a system from a second order ODE, we got the Wronskian that we've seen before, where the columns are y1 and y1 prime, and y2 and y2 prime. So that has to be non-zero, and of course there's technicalities. It might be non-zero for some special singular point in time, in which case our solution is going to be defined up to that singular point in time. Okay, so that is the end of the section on systems of ODEs. Stay tuned with us next time when we do something completely different and look at Laplace transforms.